James Webb, the baby photo machine. The clearest tool for exploring these early cosmic mysteries is the James Webb Space Telescope, sometimes nicknamed the baby photo machine for its ability to capture the universe in its youth. With its enormous mirror and unmatched sensitivity to infrared light, it allows astronomers to look back billions of years, well into the first few 100 million years after the Big Bang, when the very first galaxies were forming. In 2025, Webb continues to send down results that are rewriting expectations, showing not only individual distant galaxies, but an entire population of them, far more numerous and mature-looking than models anticipated. Surveys like Cosmology are now cataloging nearly 1 million galaxies across cosmic time and finding roughly an order of magnitude more at extreme distances than pre-launch simulations predicted. That matters because theory long suggested the early universe should have been slow to organize. Instead, Webb's data shows some of these faraway galaxies as surprisingly massive, bright, and enriched with heavy elements. In practical terms, telescopes have spotted systems that existed when the universe was still less than 1 billion years old, shining as if they had skipped ahead on the timetable. For scientists who spent decades refining cosmological models, this raises a sharp question. How could such heavy, metal-rich galaxies form so quickly? 3 leading possibilities have emerged to explain this mismatch. One idea is that the distribution of dark matter in the early universe may have included unusually dense clumps. Those clumps could have created wells of gravity strong enough to pull gas in earlier and faster, producing galaxies far ahead of the expected schedule. Another candidate explanation is that star formation itself unfolded more explosively than models assumed, with successive generations of stars being born, burning through fuel, and dying in mere tens of millions of years, seeding heavier elements into their host galaxies almost immediately. Third option is that part of what we are seeing lies in how surveys interpret faint objects at extreme redshifts, meaning some readings could be biased, and ongoing reevaluations might refine which objects are truly as massive as they appear. Even with those uncertainties, the picture Webb is painting has continuity across independent teams and approaches. Researchers measuring spectra at different wavelengths, using different analysis techniques, are all converging on the same finding: the young cosmos was more complex and varied than expected. Some early galaxies do still look small and faint, lining up with the anticipated picture, but others are dramatically oversized for their age. This diversity suggests that evolution did not proceed evenly across the universe. Some regions may have raced ahead precisely because they sat at intersections of the cosmic web where matter was particularly dense. Webb's value lies not only in imaging these ancient systems, but in measuring their physical details. Its detectors catch redshifted light, radiation stretched as the universe expands, which can then be precisely measured to determine distance and age. In many cases, spectral analysis reveals the fingerprints of heavier elements, what astronomers collectively call metals. Since metals are forged inside stars and spread when those stars explode, their early and abundant presence in galaxies only a few 100 million years after the Big Bang means star formation was already vigorous. That alone alters how scientists think about the first phases of reionization, the cosmic transition from an opaque fog to transparent space. The nickname baby photo machine comes from this power. Just as a snapshot captures a baby at an age before memory existed, Webb is providing images of the universe when it was still in its earliest stages, too young to resemble the structures we take for granted, yet undeniably already forming them. Instead of blurry, indistinct smudges, Webb produces defined structures, showing that galaxies could assemble into organized systems shockingly early. In effect, we are no longer speculating about the first galaxies, we're watching them unfold in detail. What unsettles cosmologists most is not Webb's technical prowess, but what its data imply. If massive galaxies existed so soon, then the timeline for making heavier chemical elements might need to shift earlier. Chemically enriched environments could have appeared long before previously believed. That raises speculative, but still unproven questions. If metals are already widespread at early times, then the raw ingredients needed for rocky planet formation might also have appeared earlier. But it is important to underline that this is only a possibility. No current JWST data confirms that planets or life emerged early. All we can responsibly say is that if enrichment came fast, then conditions for the building blocks may have been available sooner. That if remains large and unresolved. What is not in doubt is that Webb has deepened the tension between theory and observation. Models that once described a predictable progression toward complexity must now account for the reality of early giants. It echoes earlier moments in science when new tools disrupted consensus, Galileo's first glimpses of moons orbiting Jupiter against expectations, or Edwin Hubble's discovery of the expanding universe that overturned static cosmology. In this same tradition, the Webb telescope is exposing the shortcomings in models that had seemed reliable just a few years ago. Astronomers described the feeling in 2025 as equal parts exhilaration and frustration. Finding galaxies 10 times more numerous at early epochs than anticipated is thrilling, but it also generates more questions than answers. Each new image carries with it a new puzzle. Why this galaxy in particular? How dense was its environment? Which processes could assemble such mass in so little time? And if Webb has already found them, are there still more extreme examples? Sitting just beyond its reach? The telescope's reach is not confined to the deep past. While its flagship results spotlight the youngest galaxies, Webb also returns detailed images of local phenomena, from auroras on Jupiter to star-forming regions in the Milky Way. These serve as checks and balances, letting researchers understand physics close at hand while applying the same rules to the far universe. This dual role, studying both the nearby and the ancient, builds confidence that the strange results at high redshift are not illusions, but genuine features of cosmic history. What makes these discoveries particularly powerful is that they are not isolated. Instead, they fit into a growing catalog of consistent anomalies. Multiple spectra, across multiple sources, all indicate early activity richer than predictions. By 2025, this is not a one-off curiosity, it is a trend. That is why the baby photos matter. They turn speculation into consistent observation, demanding that theory keep pace. Science often advances this way. Surprising data surfaces, consensus falters, and eventually models adapt. Webb's catalog of unexpectedly mature galaxies is now pressuring cosmologists to rethink their assumptions about how structure formed in the early universe. Whether the solution lies in revised models of dark matter, new physics in star formation, or simply deeper refinement of observations, the process is underway. Standing back, the lesson is straightforward. The young universe was not as simple or as slow-moving as earlier models suggested. It was brighter, busier, and more uneven, with regions racing ahead while others lagged behind. That fundamental shift in our picture is Webb's greatest contribution so far, showing a cosmos that was always more dynamic than we expected. And this reimagining of the restless young universe naturally pushes us toward the next frontier. Because while Webb reveals the skies as they once were, other clues about the past have literally fallen at our feet. Ancient fragments that carry stories from long before planets like Earth ever formed. The meteorites that outsmarted Earth. When scientists talk about records left behind by the early universe, some of the most durable are not in data archives or telescope images, but in the solid form of meteorites. They are fragments of matter older than Earth itself, more than 4 billion years old, and they preserve chemical details that the young planet erased long ago. Each stone that survives a fall to Earth acts as a natural archive, storing the chemistry of the early solar system and, in some cases, the chemistry of stars that lived and died before the sun was even born. Recent fieldwork in 2025 has kept adding to this long-running archive. Teams traversing the empty white expanses of Antarctica have recovered specimens with atomic fingerprints that differ from anything found in ordinary terrestrial material. Antarctica makes an unusually good search ground. Dark meteorites are easy to spot against bright snow, and the frozen conditions preserve their interiors from contamination. For these reasons, many of the most pristine samples ever studied come from Antarctic ice fields. Some of the recent finds contain rare isotopes, arrangements of protons and neutrons that point to origins in stellar environments predating the solar system. This alone tells scientists they are handling material not shaped on Earth, but inherited from an earlier generation of stars. Fragments of iron meteorites can also display crystalline signatures unfamiliar to normal geology. One notable feature is the Wittgenstein pattern, intersecting metallic lines that only form if molten metal cools at an exceptionally slow pace over millions of years inside large parent bodies like asteroids. The Earth's environment never allows such textures to form naturally, since surface metals solidify far more quickly here. Each cross-hatch pattern is therefore a direct record of cosmic time, a marker of processes that occurred on scales much longer than human history before being frozen into a lump of iron and eventually tossed across space to reach our atmosphere. What gives these samples even more significance is their mixed heritage. Some of their isotopic contents trace back to cataclysmic stellar events, particularly supernovae. Those stellar explosions create heavy elements, iron, calcium, nitrogen, oxygen, that later become the stuff of planets and life. In meteorites examined in recent years, scientists have identified inclusions showing clear signals of pre-solar grains. These microscopic crumbs formed in ancient stars before our solar system assembled. To hold them is, in a literal sense, to hold pieces of other suns. Meteorites thus remind us that Earth is not an isolated creation, but the product of earlier stellar generations, with their ashes falling back into new planetary systems. Aside from their physics, these meteorites offer a bridge to more human ways of thinking. Some researchers describe them as cosmic family elders, pieces of matter far older than Earth that still arrive unannounced, carrying memories of the universe's earlier generations. It is a useful metaphor because it captures how meteorites extend our family tree of matter far beyond local history. They are awkward guests but carry knowledge no one else has. Naturally, the question arises, what specific information do these fragments carry that matters for life itself? Here the conversation becomes especially interesting. Laboratory studies of certain meteorites have revealed carbon-rich molecules, organic compounds much more complex than simple arrangements of hydrogen and carbon, but still far short of life. These compounds look like plausible precursors, molecules capable of linking up under the right conditions and forming the chain central to amino acids or nucleic acids. They represent chemistry leaning in the same direction as biology. This finding matters because it broadens how we think about life's origin. If meteorites routinely contain such molecules, it suggests that chemistry that eventually produced life on Earth was not unique to our planet, but common in interstellar space. Space itself is capable of manufacturing part of biology's toolkit. Life still required the special setting of liquid water, energy, and stability on Earth, but the raw ingredients could have arrived long before, delivered by falling stones. Scientists speak cautiously, but these organics are plausible contributors to early Earth's feedstock, supporting the idea of panspermia, or seeding as one viable pathway among several for life's beginnings. Confirming such claims requires careful laboratory methods. Researchers take measures to separate meteoritic interiors from the surfaces that touch air, soil, or ice. Chemical and isotopic analyses then sort what is truly extraterrestrial from what could have seeped in after impact. When unusual isotopic ratios appear, those that do not match any known terrestrial pattern, they give confidence that the molecules really came from space. The new finds of 2025 have provided exactly this sort of evidence, indicating unmistakable extraterrestrial organics preserved inside rocks since before Earth itself existed. One can imagine this process in very practical terms. Early Earth, still hot and unstable, was bombarded by countless comets and asteroids. Many of those carried the same types of compounds we detect now. Each impact would have scattered materials, some of which dissolved into pools of water, where energy from sunlight, lightning, or geothermal heat could drive further reactions. In this picture, meteorites acted like couriers, dropping off packets of chemistry that the young planet could then store, rearrange, and build upon. They did not guarantee life, but they widened the field of possibility dramatically. The broader implication is equally striking. If space routinely manufactures and delivers these molecules, then other young planetary systems elsewhere likely experience the same deliveries. The recipes for prebiotic chemistry may be dispersed across the galaxy rather than restricted to our neighborhood. This makes the probability of life elsewhere higher, not certain, but less dependent on Earth having been an exception. The meteorites therefore tie nicely into the wider search for habitability on exoplanets, giving researchers reason to expect that complex chemistry should exist wherever stony bodies orbit new stars. Practical challenges remain in studying them. How do scientists know the molecules inside a blackened rock in a desert are not just residues from soil or rain? The answer lies mainly in preservation environments. Antarctic meteorites become encased in ice and often remain untouched for thousands of years before researchers collect them. Desert meteorites, when carefully excavated, can be cleaned and sliced to access untouched interiors. These strategies ensure the organics measured today represent space chemistry rather than Earth contamination. The paradox here is that some of the harshest, most lifeless landscapes on Earth, the dry expanses of deserts and the frozen plains of Antarctica, are exactly where we find the best evidence for how life's chemistry might have begun. A frozen horizon may look empty, but scattered across its surface are fragments that carry history written in isotopes and carbon chains. These records are not vague suggestions, but tangible artifacts, evidence that our planet's molecules were shaped by wider forces operating long before there was a planet to stand on. This is why meteorites are said to outsmart Earth. They contain structures and chemical stories our planet erased during its violent youth. They preserve compounds our environment could not make or could not protect for billions of years. They reach across cosmic history to deliver not certainty but strong clues that the building blocks of life existed long before the ground beneath our feet was solid. In our hands, they are the most direct proof that cosmic matter carries memory. And just as they push us to rethink origins, other mysteries of the universe push even harder, raising questions not about beginnings but endings, and whether reality itself is capable of remembering anything at all. The black hole paradox. Physicists face another frontier that tests the limits of what we call reality itself, the black hole information paradox. For nearly 50 years, this puzzle has stood as a direct clash between the two most reliable frameworks in science. General relativity, which describes how gravity bends space and time, suggests that when matter falls through a black hole's event horizon, the information about it disappears forever. Quantum mechanics, by contrast, insists that information about any physical system must always be conserved. The paradox arises because both frameworks cannot be correct in this case, and yet both have proven astonishingly successful everywhere else. Stephen Hawking's original calculations made the conflict unavoidable. He showed that black holes are not completely black, but slowly emit radiation known as Hawking radiation. The problem is that this radiation is thermal, meaning it looks random and carries no imprint of the matter that fell in. Taken at face value, this implies information is lost, wiped from existence. That conclusion broke with quantum mechanics' strict conservation rule and created a split in physics: either accept that black holes shred records forever, or concede that something deeper must be going on. For decades, the debate remained frozen at this impasse, with neither side yielding. Instead of being a question confined to whiteboards, researchers now attempt to model pieces of the paradox using quantum processors. These are not full simulations of an astrophysical black hole, but carefully designed toy models, simplified frameworks that capture specific aspects of quantum gravity. Quantum computers happen to be well suited to this task. Because they naturally exploit superposition and entanglement, the same features believed to govern matter near an event horizon. For the first time, scientists are watching how entangled particles behave when one partner falls into a simulated black hole while the other remains outside. So far, the results are suggestive rather than decisive. Early simulations point to a possibility long theorized. Information may not be destroyed, but scrambled into correlations hidden within the Hawking radiation, so fine and dispersed that no realistic observer could ever decode them. In principle, at least, the data is not erased. It exists in a form so scrambled that it is effectively lost to practice. This reframes the debate. The core question is no longer just destroy or preserve, but whether preservation that is impossible to access should still count as a solution to the paradox. A useful analogy is burning a book. To the human eye, the book is gone, reduced to ash, heat, and smoke. Yet physics holds that the microscopic details of the flame, the molecules dispersed in the air, and the vibrations imparted to the environment contain the full record of what was burned. The information is conserved, but so hopelessly scattered that reconstruction is practically impossible. Toy model black holes generated on quantum computers might behave in similar fashion. They would act less as obliterators and more like machines encoding data into nearly unreachable complexity. This line of reasoning offers a partial way out of Hawking's original conclusion. If, theoretically, the fine structure of Hawking radiation encodes the information, then physics retains consistency. No part of reality then permits true erasure. But for a real observer, the effect is the same as destruction. Even with unlimited patience, the correlations are so faint they cannot be reassembled. In practice, we are confronted with a kind of effective loss. That slippery distinction, conserved in principle, unrecoverable in practice, is at the heart of current research. Quantum entanglement complicates matters further. Some simulations indicate that particles crossing the horizon may preserve subtle correlations with partners left outside, suggesting the horizon is not a sharp cut but a permeable filter. Instead of information plunging past a one-way barrier, it might be smeared across the boundary through entanglement that challenges the simple image of a black hole as a sealed void and instead portrays it as part of a wider web, interconnected with the universe beyond. Skepticism remains necessary. These are not astrophysical black holes, but mathematical constructs running on current quantum processors. Modern devices can only manage systems of modest size, nothing close to the billions of particles involved in reality. The simulations capture patterns and principles, not the full complexity of collapsing stars. At best, they provide hints, clues about how information might be managed by nature, not proofs of what nature actually does on cosmic scales. For that reason, physicists emphasize caution. Intriguing signals in laboratory models may not survive translation into full theory. Even so, the progress matters. For decades, the paradox lingered as a theoretical wound, unsolvable because of the incompatibility of general relativity and quantum mechanics. By bringing actual computations into the mix, the debate takes on a more experimental character. New generations of quantum processors become laboratories for questions once thought untestable. By itself, that shift represents a step forward. The paradox is no longer just an argument about logic, but a question accessible to empirical methods. If these approaches prove sound, they may restore a reassuring principle that the laws of physics do not permit complete erasure. If black holes preserve everything, then in principle the universe contains a permanent record of all events, no matter how well hidden. That deepens the mystery of causality, because information released after eons would still be part of the chain of cause and effect. Our usual sense of time, as a straightforward arrow from past to future, grows cloudy under such a framework. One way to illustrate this is to ask, if information is preserved but emerges billions of years later in scrambled radiation, what does that imply for sequences of cause and effect? The idea raises uncomfortable possibilities. Could the future contain echoes strong enough to force revisions of the past? Not in practice, but conceptually, the neat division we rely on. The past is fixed, the future is open, becomes less clean. The question reaches toward free will, determinism, and the role of information in defining what events can unfold. Yet it is important not to leap into sharp conclusions. The toy model results are only the first probes into a question many expected to remain impenetrable. Even as we consider their implications for time and causality, the field remains careful not to declare the paradox solved. More accurate simulations, stronger theories, and deeper experiments will be needed before black holes can be said to have revealed their secrets. The paradox endures as part of a wider struggle, reconciling our best descriptions of gravity with our best descriptions of the quantum. For now, black holes continue to act like signposts marking the place where these two theories break down. They highlight the limits of our knowledge, and in doing so keep science anchored to its most fundamental mystery: what rules truly govern the universe at its extremes. As the research advances, the narrative of 2025 is defined by cautious opportunity. Quantum processors provide a new toolkit. Early evidence points toward deep encoding rather than outright destruction, and the conversation has shifted from philosophy to something closer to experiment. No decisive solution exists yet, but a path has opened. The implications for physics are enormous, but so too are the implications for how we think about time, memory, and determinism. And once questions of information, history, and causality emerge, another possibility presses in from theory. Some researchers argue that the equations themselves point toward realities even stranger than hidden records within black holes. There may be more than one universe altogether, and signs of those possibilities may already be hiding in the data we collect today.